Have you ever let go of a blown-up balloon and watched it zoom around the room? That wild flight is your own mini rocket in action. The air rushing out pushes the balloon in the opposite direction, a perfect example of how rockets work. Now imagine scaling up that idea, a giant rocket towering over buildings, ready to blast off into space. But how does something so heavy break free from Earth's grip? That's the big question at the heart of rocket science. The answer lies in understanding the forces that move things and how we can use them to reach the stars. From a squealing balloon to a soaring rocket, we'll break down the science that makes space travel possible. Ready for liftoff? Let's dive into the world of rockets. Before a rocket can soar into the sky, it must first defeat its biggest and most relentless enemy, gravity. This invisible force is always present, quietly working against anything that tries to leave the ground. Gravity is the unseen force pulling everything towards Earth's center. It's the reason we stay firmly planted on the ground, why dropped objects fall, and why the planets orbit the sun. It's everywhere, affecting everything with mass. For rockets, gravity is like climbing an endless, impossibly steep hill that never gets any easier. Every meter upward is a struggle against this powerful pull. Rockets are incredibly heavy, sometimes weighing millions of kilograms, so gravity's grip on them is enormous. The bigger the rocket, the harder gravity pulls it down. To lift off, a rocket must generate a force, called thrust, that's greater than its own weight. This is no small feat. It takes immense power to break free. Imagine trying to lift a car above your head. Your muscles simply can't match gravity's pull. Rockets need engines powerful enough to do just that, but on a much larger scale. The engines must push harder than gravity pulls, especially at launch, when the rocket is at its heaviest and fully loaded with fuel. This battle against gravity uses up most of the rocket's energy and fuel. That's why rockets carry so much fuel, just to escape Earth's grip. Only when the upward push finally beats gravity does the rocket begin its climb into the sky, leaving the ground behind. That's why rocket engines are so massive and why every launch is such a dramatic, awe-inspiring event. Overcoming gravity is the very first and toughest step in any space mission. It's a challenge that demands precision, power, and determination. Every rocket launch is a victory over Earth's invisible grip, a testament to human ingenuity and perseverance. That's the challenge every space mission must conquer before it can reach for the stars. Lifting off is just the start. To truly escape Earth, a rocket must reach escape velocity, the speed needed to break free from gravity forever. For Earth, that's about 11.2 kilometers per second, faster than anything you've ever seen. Imagine throwing a ball so hard it never comes back down. That's what rockets aim for. But rockets don't hit this speed instantly. They accelerate, fighting gravity and air resistance as they climb. Most rockets don't need to escape Earth completely. They just need to reach orbit. Getting into orbit still means going incredibly fast, but not quite escape velocity. The engines keep firing, pushing the rocket faster and higher until it reaches the right speed. It's a marathon, not a sprint. Constant acceleration is key. Whether escaping or orbiting, speed is everything. The real race is against gravity's relentless pull. Only by reaching these incredible speeds can rockets leave Earth behind. That's the secret to space travel. So how do rockets create the force to fight gravity and soar into the sky? What's the secret behind their incredible power? It all comes down to Newton's third law, one of the most important ideas in physics. For every action, there's an equal and opposite reaction. This law explains not just rockets, but so many things we see every day. When you let go of a balloon, air rushes out one way and the balloon zips the other way. It's a fun, simple example of Newton's law in action. Rockets work the same way, but on a massive scale, using powerful engines and tons of fuel to create huge forces. Inside the engine, fuel burns rapidly, creating extremely hot gas that's blasted out the nozzle at incredible speeds. The action is the gas shooting downward, forced out by the burning fuel. The reaction? The rocket is pushed upward with tremendous force. This is what we call thrust, and it's what lifts rockets off the ground. Unlike cars, which rely on pushing against the ground or air, Rockets don't need anything beneath them to push off from. Instead, they push against their own exhaust, making them unique among vehicles. That's why rockets work perfectly in space, where there's nothing to push against. No air, no ground, just emptiness. As long as there's fuel to burn and gas to throw out, a rocket can move anywhere in the universe, from Earth to the farthest planets. This simple law is the foundation of all space travel, making exploration of the cosmos possible. It's why rockets can launch from Earth, escape gravity, and maneuver in the vacuum of space with precision. Newton's third law turns burning fuel into motion, transforming chemical energy into the force that powers space exploration. Every rocket launch is a real-life demonstration of this powerful principle, witnessed by millions around the world. That's the magic behind every blastoff, the science that turns dreams of space into reality. Action and reaction, it's rocket science made simple, and it's the key to reaching the stars. To create the massive push needed for space travel, rockets use special fuel, much more powerful than car petrol. This fuel is engineered to release an enormous amount of energy in a very short time, far beyond what everyday fuels can provide. It's the difference between a gentle nudge and a thunderous blast that can break free from Earth's gravity. Rocket engines are essentially controlled explosions, burning fuel and an oxidizer to make hot gas. This hot gas is forced out of the engine nozzle at incredible speeds, creating the thrust that propels the rocket upward. The process is violent, precise, and absolutely essential for launch. The oxidizer provides oxygen, since there's none in space. Without it, the fuel couldn't burn once the rocket leaves the atmosphere. That's why rockets must carry their own supply. Rockets carry both fuel and oxidizer in separate tanks, mixing them only in the engine. This careful separation is crucial for safety and efficiency, preventing accidental ignition before launch. There are two main types of rocket fuel, liquid and solid. Each type has unique properties and is chosen based on the mission's needs. Liquid fuel rockets use super cold liquids, allowing engines to be turned on, off, or throttled for control. This flexibility makes them ideal for missions that require precise maneuvers or multiple engine burns. Solid fuel rockets have fuel and oxidizer mixed together in a solid form. Once lit, they burn until empty. They're simple, reliable, and can sit ready for long periods. Solid rockets are simple and powerful, but can't be shut off mid-flight. Their unstoppable burn delivers a huge initial boost, but offers no control once ignited. Many rockets use both types, solid for initial thrust, liquid for control and precision. This combination takes advantage of the strengths of each fuel type. This combination gives flexibility and power for different mission stages, letting rockets adapt as they climb higher and faster. The right fuel mix is crucial for reaching space. Engineers spend years perfecting these formulas to maximize performance and safety. Every launch is a careful balance of energy, weight, and control. Even a small change in fuel or design can make the difference between success and failure. That's how rockets get the ultimate push to leave Earth, overcoming gravity with a perfect blend of science and engineering. Fuel choice is at the heart of rocket design, shaping every mission from the ground up. Ever notice rockets look like stacked cylinders? Those are stages, a clever way to shed weight as the rocket climbs. Most of a rocket's weight at launch is fuel. As it burns, empty tanks become dead weight. Staging lets rockets drop empty sections, making the rest lighter and easier to accelerate. The first stage is the biggest, lifting the rocket through thick atmosphere. Once empty, it's jettisoned. The next stage ignites, pushing the now lighter rocket even faster. Some rockets have 3 or more stages, each one firing and dropping away. This step-by-step shedding is like tossing empty bottles from a heavy backpack on a long hike. By the time the final stage fires, only the payload, satellite or crew remains. Staging is key to reaching orbit efficiently. It's rocket science's ultimate weight loss trick. To orbit Earth, rockets don't just go straight up. They need huge sideways speed. After launch, rockets tilt and turn, flying more horizontally. This is called a gravity turn. Imagine throwing a stone so fast that as it falls, Earth curves away beneath it. It never lands. That's what being in orbit means, falling around Earth, not into it. Astronauts in the International Space Station are in constant freefall, moving sideways at 28,000 kilometers per hour. Rockets first climb to escape thick air, then turn sideways to build up orbital speed. Once at the right altitude and speed, engines shut off. The spacecraft is now in orbit. It's caught by gravity, but moving fast enough to never fall back. Orbiting is a delicate balance of speed and altitude. That's how satellites and astronauts circle our planet. How do rockets work in space where there's no air? Unlike planes or birds, rockets don't need air to push against. They carry both fuel and oxidizer, making them self-contained. The engine throws hot gas out the nozzle. The reaction pushes the rocket forward. This works even better in space, where there's no air pressure to slow the exhaust. In a vacuum, exhaust gases expand freely, making rockets slightly more efficient. That's why rockets can maneuver in deep space long after leaving Earth. Small thrusters let spacecraft steer, change orbits, or head to other planets. Rockets thrive in the airless void thanks to Newton's third law. No air, no problem. Rockets make their own push. This principle powers every journey beyond our atmosphere. Space travel is possible because rockets bring everything they need. Rocket science isn't just theory, it's happening right here in India. ISRO's PSLV rocket is a perfect example. The PSLV uses 4 stages and a mix of solid and liquid fuels, shedding weight as it climbs. Its powerful first stage and strap-on boosters provide the initial thrust, followed by precise, liquid-fueled stages. The PSLV launched Chandrayaan-1, India's first moon mission, discovering water on the lunar surface. Each stage, each engine, and every bit of planning shows how science and engineering come together. The PSLV proves that with teamwork and innovation, we can reach for the stars. Rocket science is a puzzle we can solve, one launch at a time. India's rockets inspire us all to dream big and aim higher.